Let's talk about the solubility equilibrium. Even though we classify some compounds are insoluble in water, but they are slightly soluble in water. So under this chapter, we talk about the solubility of these partially soluble compounds or the solids in water. So what is Ksp? Ksp is called the equilibrium constant for solubility product. Um, so this the magnitude of the Ksp tells us how or how much this compound is going to be soluble in water, whether is it like a highly soluble product or whether it is slightly soluble or if it is completely. Oh, is it too hard to make it soluble? Yes, we get all this information from the magnitude of this Ksp. So let's see how we can calculate this Ksp. Ksp equal to it's a equilibrium constant. So like how we have calculated the equilibrium constants under equilibrium chapter, it also applies here the same theory. So this Ksp equals to the concentration of the products over the concentration of the multiplication of the concentration of the reactants raised to its coefficient from the balanced chemical equation. Let's talk about how we can write the Ksp for this equilibrium. This is the solvation of the or um, dissolution of the silver chloride in water. So it is a slightly soluble compound, so it makes an equilibrium. So it dissociates into silver plus ions and chloride minus ions. So how do we write the equilibrium constant? Yes, equilibrium constant equals to the concentration of the products, the multiplication of the concentration of the product divided by the concentration of the reactant. Since this is a solid, so now we know that the concentration of the solid is a constant. Therefore, we can apply a modified equilibrium constant. So here is that the modified equilibrium constant, which is known as the solubility product constant, which is only equals to the product of the or the multiplication of the concentration of the products raised to the coefficient from the balanced chemical equation. So in case P, we only include the concentration of the product. Since the concentration of the reactant is a solid, so the physical state of the reactant is a solid, so we don't include that in the Ksp equation. If this Ksp value is smaller, it is less soluble. If the Ksp is relatively larger value, then solubility of that solid is greater. Right. How we can express the solubility of a product? Yes, there are two ways. We can express the solubility using molar solubility, that can be defined as the number of moles of the solute in 1 liter of the saturated solution, or the solubility. Solubility is the number of grams of solute in 1 liter of saturated solution. So you can either express the solubility in either in with molar solubility or with solubility. Both refers to the concentration at 25 degrees of Celsius. How do we solve a problem with KSP? Yes, we follow the same procedure we learned under equilibrium. First, we construct that ice table. Then we fill that table with what we know. Then we construct an equilibrium equation to solve for the unknown factor. Right, here is an example. Calculation of Ksp, calculation of the molar solubility and solubility for silver bromide. We are given the Ksp for the silver bromide is equal to 7.7 times 10 to the negative 13. So now we need to find the molar solubility and solubility. So we write the equation. When we write the equation, we balance chemical equation for the dissociation of silver bromide in water into silver ions and the bromide ions. So when we balance it, it is 1 to 1 ratio. So we refer the equilibrium concentration as S. Then the initial concentrations are 0, and the change of concentration we taken as plus S for silver ions, again plus S for bromide ion because stoichiometry is equal there, and the equilibrium concentration for silver ions is just S, and the equilibrium concentration for bromide ion is also S. Then we write the equilibrium expression as Ksp equals the concentration of silver ions, equilibrium concentration of the silver plus ions multiplied by the equilibrium concentration of the bromide ions. Right. Then we are given the Ksp value, so we plug that here and it equals to S squared. So in order to solve for S, we get the square root of that compound, number, and the solubility was obtained as 8.8. Molar solubility is obtained as 8.8 times 10 to the negative 7th molar. Right. So now we need to express the solubility. So the solubility must be expressed in grams per liter. So then we need to multiply this molar solubility by the molar mass of that compound. So the molar mass of this silver bromide is 187.8. So we multiply this molar solubility by the molar mass of it, and we obtain the solubility as 1.7 times 10 to the negative 4th grams per mole. Right, so this is the molar solubility, and here is the solubility of silver bromide. Practice problem 1. Right, so in this lecture, some students have asked me to show the work for some problems. So with this lecture, I have included for each lecture, I included lots of practice problems with work and the answer. So please follow these videos if you want to if you need to know the work, or if you need to know how the answer was obtained. Practice problem 1. Calculate the solubility of copper 2 hydroxide. Right, so this is solubility. We are asked to find the solubility. So we need to get the answer in grams per liter. Right. Next, okay, let's try to solve this. So first thing we need to write this equation, dissociation of copper hydroxide to copper 2 plus ions and hydroxyl ions. Right. So then we write the Ksp. We need to square the concentration of hydroxide ions to the power of 2, and the Ksp is equal to 2.2 times 10 to the negative 20th, and the molar mass for this copper hydroxide is 97.57. Those are the information we have. That's what we should set up before we solve the this problem. Right. Let the solution. So Now first we need to find the molar solubility using the Ksp of the um, copper hydroxide. So in order to solve that, we need to set up the ice table. Right. So initial concentrations of the copper 2 plus and hydroxide ions are zero. Change in concentration. If the molar solubility of copper 2 plus is S, then it would be change. The change for the hydroxide ions would be 2S because of this coefficient. So the equilibrium concentrations for copper 2 plus will be S, and equilibrium concentration for hydroxide ions will be 2S. We plug those values into our Ksp equation. So it is S times 2S squared, because in the equilibrium equation we need to raise to the power of its coefficient in the balanced chemical equation. So we get the Ksp equals to 4S cubic. So we need to solve for the S. First, we need to divide this number by 4, then get the cubic root of that answer. That will be equal to the molar solubility. Here is the answer, 1.8 times 10 to the negative 7th. Then, in order to get the solubility, we need to multiply the molar solubility by its molar mass, and we get the solubility of copper hydroxide as 1.7 times 10 to the negative 5th grams per liter. Next thing, the solubility of the practice problem 2. The solubility of calcium sulfate is measured experimentally and found to be 0.67 grams per liter. Calculate the value of Ksp for calcium sulfate. The molar mass of calcium sulfate is 136 grams per molar. So we cannot do anything with the solubility. We need to change that to the molar solubility. So we need the molar mass of calcium sulfate. So we divide the solubility by its molar mass. So here is the molar solubility, 4.9 times 10 to the negative third moles per liter. In order to find the Ksp, we need to write the balanced chemical equation for the dissociation of calcium sulfate into its ions in water. So Ksp can be written as the multiplication of the concentration of the calcium 2 ions by multiplied by the concentration of the sulfate ions. So Ksp equals S squared, and it is obtained as 2.4 times 10 to the negative fifth. Look, the exponent now is a really small value, 10 to the negative fifth, but normally we get 10 to the 20, 10 to the 10th, like that. So this is actually relatively a large Ksp value.